Hey there, my name's Gary Sims and this is Gary Explains. Now, I really hope you've had a chance to watch my Arduino versus Pico video. If you did, you will know that the microcontroller chip at the heart of the Raspberry Pi Pico is actually for sale as a separate component. And that means that other manufacturers can design microcontroller boards using the same chip, the RP2040, which of course is a dual core Cortex M0 Plus processor with 264K of RAM, and they can make their own boards on it and actually add more interesting features. And that's what we're going to look at today. The Challenger 2040 board comes not only with the RP2040, so it's the dual core, as I said, M0 Plus CPUs, but it's also got Wi-Fi and Bluetooth using an ESP-32 board, plus a whole bunch of other features. And it works with MicroPython, CircuitPython, and with the Arduino, and with the Raspberry Pi Pico C and C++ SDK. In fact, you can program this thing almost any way that you want. So if you want to find out more, please let me explain. Now, one of the key features of the Challenger 2040 board is it does offer Wi-Fi and Bluetooth, something you don't get on the standard Raspberry Pi Pico. You do get it on the Raspberry Pi Pico W. This is a different way of doing it, but it's also got a whole bunch of other things that make it quite an interesting and unique board. Let's have a look at some of the features. So here is the Challenger RP2040 board, and at its center is the RP Raspberry Pi 2040, the microcontroller from the Raspberry Pi Foundation with those two Cortex M0 Plus CPUs and 264K of RAM. However, it's not only about that. If it was just about that, then this would just be a copy of the Raspberry Pi Pico, but there's more. And let's start here at the connector, the USB-C connector. So actually, I've kind of almost migrated over fully to USB-C with just about everything I've got here in my house, and I actually have to dig out an older cable if I want to use the Raspberry Pi Pico. Seeing USB-C here is a good step forward. And then another interesting thing you have here is this battery connector and the corresponding LiPo charger circuit. So the idea, of course, is that you can run this from a battery, and the battery can be charged up when it's plugged in, and then you can kind of go off and just use it when it's not plugged into the mains, but it's running on the battery, just like you would charge, you know, tablets, phones, or whatever. So a great feature already built into the board, which gives you as a creator, as a maker, the opportunity to make portable devices that you know you charge up, and you can take them away and use them and do whatever it is you're going to do with them. And there's 8 megabytes of flash. This is compared to the 2 megabytes of flash you'd get in a Raspberry Pi Pico. 8 megabytes of flash, and so that gives you optimal room for user interfaces, for media, for any other storage you need to put on there, already built in there on the board. And of course, there is the Wi-Fi and Bluetooth, and that is via an ESP32C3 chip. Maybe that is worth talking about, this whole dynamic between having two chips on the board, because that itself has a CPU and memory and RAM. And maybe if you're interested in that dynamic, tell me and I'll make a separate video about it. But that provides all the Wi-Fi and the Bluetooth, and the RP2040 talks to the ESP32 chip, and they kind of say, let's set up the Wi-Fi, let's join this, here's some data coming, and they kind of just chat to each other. So all that Wi-Fi stuff is all handled by a different chip, leaving the RP2040 free to do whatever it is that you want it to do. All it needs to do is interrogate that other chip and say, hey, give me the data that's coming over the airwaves. And there's also a NeoPixel, which is great because it's great having one LED, which this one has as well. It's over there by that USB-C behind it there, between the battery and the USB-C. It's great having one of those, but often it's like, I wish I could have two or three more to actually tell me what's going on. Here we've got an RGB one, so you can change the color. And one of the demos I'm going to show you is I change the color of the pixel as it goes through different states, like powering up and connecting to the Wi-Fi, and then getting synchronization for the time, which is one of the projects I'm going to show you. And it changes the LED as it goes along, so it's a really good way of communicating the status of the board. And then finally, there's 2 buttons on here. On the normal Pico, you'd only get a boot button. We also get a reset button built in. So it's all these little things, just USB-C, you get a reset button. You've got this pixel chart, you've got this pixel, NeoPixel, you've got the 8 megabytes of flash, of course you've got Bluetooth. It's all these extra things that add up to make this a really versatile board. Okay, so now we can see it's got quite a rich feature set. Let's have a look at some of the demos using Wi-Fi, using the NeoPixel and so on, across all the different ecosystems, MicroPython, CircuitPython, Arduino and so on. Okay, so first of all, let's look at how you change the NeoPixel with CircuitPython. I've also got an example on my GitHub repository on how you do this with MicroPython, and that's using the standard MicroPython that you would use for the Raspberry Pi Pico, because of course it's completely compatible. So what you need to do is go over here to CircuitPython. I've used version 7, there is a version 8 available, but still in early days. You download the UF2 file, and then what you do is you reboot your Challenger board by pressing down the boot button and then either plugging it in or pressing the reset button. That will make it appear as a drive on your PC, and then you just drag the UF2 file to it, and that's it. It downloads and installs the UF2 file onto the CircuitPython, onto the board, and then when you reset it, you've actually got Python running there. So let's look at some Python code. Okay, so on CircuitPython, you want to create a file called code.py, P for Python. And this code here, it's the stuff that the Adafruit people have done. I've modified it a bit, of course, kept all of the copyrights and everything. And so basically there's a couple of functions here at the top which are just to do with colors, because we're going to cycle through some colors because that makes it look nice. And wheel and rainbow cycle, just fiddle with that. You can just look at it. It's basically red, green, blue stuff. You don't need to worry about it too much, but interesting to look at it if you want to. And the way you use it is you say pixels is equal to neopixel.neopixel, and that's all built into CircuitPython, so you don't need to do anything extra. Just need to do some imports here up at the top. For example, there's import of neopixel, and you need to give it the number. Now, the pinouts on the Challenger board are different to that on the Raspberry Pi Pico, so you need to check the pinout diagram, and you need to notice that the neopixel is on GP11. So that's what I put in there. Number of pixels is 1, because of course neopixels can be a whole LED strip. There's just one of these here. And basically at the same time, we're also going to flash the LED that's on the board itself, and that's attached to D13. Okay, very simple. All we do is we say fill the pixels with 2555, 2550 to start with, turn the light on, the LED on the board, go through all the different colors, okay, which does this one here, and it fills them with different colors according to the red, green, blue that gets returned here from the wheel function. Just cycles through the colors basically. Then we turn the LED off, and then we do the same thing again, and then we loop. So basically the green LED on the board will flash on and off once every 2 seconds or 3 seconds or something, because this one goes through all the different colors. So this kind of acts as a delay if it was a normal flash blink program, but actually what it's doing is cycling through all the colors on the neopixel, and then that's it. So it's a very, very simple piece of CircuitPython code, and it just shows you how you can access the neopixel, and it works just absolutely great. Now, the next bit of code I want to show you is how you can run a kind of time synchronization over the internet, how you can power a small OLED display with the SSD 1306 driver. I cover that in a few other videos here, and how you can use the ESP, remember it's an ESP32 chip that's doing the Wi-Fi stuff. So ESP-AT control is a library that allows you to talk to the Wi-Fi and get all the Wi-Fi stuff up and running. And what we're actually do is we're going to connect to this website called worldtimeapi.org. Now, worldtimeapi.org is a really great website. Basically, you can just request with HTTP a time zone, and it will just give you back all this information, including the current time, including when daylight saving starts and stops, what time zone you're in, and all that kind of stuff. So it's really, really good. And there's a whole bunch of examples of what you have to do to call to get different things. There's a specification which defines all the different bits that you can access, all the different URLs you call and what they do. Really, really well done. And we're going to use it. We're going to actually just request a URL, and it will bring us back in JSON some of this time information, and then we basically sync up the real-time clock on the board. And one thing to note, this isn't a commercial service, so they have some stuff in the FAQs about this is great for hobbyists, great for if you want to try it, but don't use it for a commercial service. But what we want to do, it works absolutely great. So first of all, we've got this function called sync time with worldtimeapi.org. Okay, and that basically, if you can look in it here, it basically goes off, gets some JSON at this HTTP, which is basically based on your IP address, does the geolocation stuff, works out where you are in the world based on your IP address, and then gives you the current time and time zone for where you are. You can specify time zones in here according to that API, or just go and look up in the documentation there. Once you get the JSON back, you just need to parse it, and in here we can get the minutes and the seconds and the day and the year and the month, all that stuff out there. You can even get things like the day of the week, anything that's in the JSON. And then basically one of the parameters that's passing is the real-time clock, and we'll look at that in a second. And you basically just say, well, create me a time structure that's got all the bits in it, hours, minutes, second, daylight saving, and then just set the time. So now the real-time clock on the board is actually set to the correct date and time. Remember, we're also using this OLED display, so this is an I2C. So basically you set up an I2C, you call the function to initialize the SSD 1306 driver. As I said, I've covered that in other things. And basically to do it, you fill the display. It's a pixel-based display. You fill all the display, you write some text in. There's a font file you need that you'll find in my GitHub repository, and then you show the text you've written. So it's basically bit-based. The text is created according to a font. And so as we go through, the very first things we put in it, ... on the screen. Okay, now here is the creation of the real-time clock, RTC, which is something that we import here. So it's part of the board setup, the real-time clock. Okay, and then we need to try to connect to the internet, and you use this file called secrets.py. So secrets.py looks like this. It's basically a structure that contains the name of your SSID and your password. You would put in here your SSID and your Wi-Fi password. It takes them out of there. That means you don't have to include it in this code here, which means you can publish it and do changes to it and all that and not worry about the secrets. You just need to change that for your thing. If this is a Challenger board, which it is, there's some code here for how you set up the stuff for the Wi-Fi talking to the ESP chip. Okay, if it's not, you do this way. Basically, I left this code. This is a template code that you get. Left this code in here. It would work on other ESP boards as well, but we are, of course, using the Challenger one. And then at this point now, I say, let's change the display to connect. And at this point, it's now going to actually try to connect. There you go, Wi-Fi Manager. Actually try to connect to the Wi-Fi network. And once that's done, okay, it will then put sync ... on the screen, and then it will call our sync function, which we've just called up here, which then calls world time API, gets the JSON back, and then parses it. And once you do that, you then just go into a loop here that just shows the time on the screen. Look, you've got the OLED fill, OLED text, OLED show. Now the only little thing in here is I've also got this counter, force sync counter, which every 85,000 times it will force another sync. Now one of the parameters of sync is whether it should be blocking or not, which basically means if it fails, it won't just sit there going, oh, I'm still waiting to get an answer back, I'm still waiting to get an answer back. It will carry on. So the RTC, the real-time clock, will just stay as it was, and it will try again next time to synchronize it. And this basically means you can actually have this board up and running. You've got the real-time clock, and then once a day it will also check to make sure that the time is in sync. And this will just go round and around displaying the time on the board. And so that's a really, really interesting way showing how to use an I2C display and how to access over the internet, to get something over the internet in JSON and parse it. So that's a great boilerplate code there for just lots and lots of different types of projects that you might want to do. Now, if you remember also, the Challenger board works with the Arduino IDE, and there is a project called Arduino Pico, and this basically allows Arduino to run on the Raspberry Pi Pico and on lots of boards based on. Look at all these boards that are listed here, and of course we're using this one, the Invicta Labs Challenger RP2040 Wi-Fi and Bluetooth. Lots of other boards here. Now here's the full instructions on how you set this up inside of Arduino, exactly what you need to type in and where. I'm not going to go through all that there because it's pretty easily explained. But once you've got that set up, you now have board support for the Challenger board inside of Arduino. Okay, so here I am in Arduino with all that board support stuff set up. There's some requirements that you're going to need here. You need to make sure you get all those libraries and install them. What are they? Basically the board support, as I was just showing you, the NeoPixel library, the Wi-Fi ESP-AT, which is the library that allows you to talk to that other chip and set up all the Wi-Fi, the time library, and the ESP-AT MQTT library. If you don't know what MQTT is, I've got a couple of videos there about that here on this channel, and we're only using this because it's also got an NTP function in that library, and we're just going to use the NTP function. Makes it pretty easy. Also notice, because the Challenger board has an AT firmware, that's for the ESP32 board, greater than 2.1, you need to make sure that you comment out this line here in this file here. Just follow these instructions and it will work. If you don't do that, the Wi-Fi won't work properly. So it's basically because there are different versions and you have to basically tell it which one it's using. Also, if you want to turn off the debug statements, there's too much stuff coming out of your console, follow that instruction there. All this will be in my GitHub repository, so you can just follow it through and make sure you've got all the right library. So basically what we've got here is we've defined basically your SSID and your password. We want to set up the NeoPixel, and we want to know it's on pin D14. Notice that's different to what I was showing you in CircuitPython, because depending on whether you're using CircuitPython, MicroPython, or Arduino, you've got to use different naming, but the pinout diagram they give you covers all of the different variations. And basically you want to define your time zone, because we're just doing straight NTP stuff now. We're not going to do anything to a clever service like what we're just going to get back UTC time. And this is a very crude method here of just saying what time zone you're in. Might not work for time zones that have half-an-hour increments or even 45-minute increments. It could be expanded, it wouldn't be too hard, but this is just a simple idea to show you how it works. Set Neo basically is a function to set the pixel color to a red, green, blue value. Very simple. Now in the setup loop, we want to first of all set up the pixel to be a kind of white, so we know that things have started, everything is white to start with. You then basically need to connect to the Wi-Fi chip, make sure it's all working. If there are an error, there it goes red. Okay, and then if it can't communicate with the module, again, it just goes a different color there, whatever I've set it to be, with a red, green, so without any blue in it there. And then once we know that everything's working, we set it to green, to blue, sorry, so that we know we're now in the stage which is trying to connect to the network. Once it's connected, we set up this MQTT library, basically because we want to get the NTP time. Once we get the NTP time, we then set up a web server. Where's that defined? Let me have a look. Here it is, missed it at the very top there, web server on port 80. Again, this is all part of the standard Arduino library stuff you get. And once you go into a loop, this basically loops around waiting for requests. As you can see, it sends back HTTP and HTML here. So it's a web server. When you get a connection, it will just play back the time. And we can see that here in this print line of the time. So just a text variation of the time just gets displayed on the screen. So you're basically now, this will show you how to use a Challenger to A, connect to the Wi-Fi, B, use the NeoPixel to control different things, C, connect to NTP to get the right current time from it, and then finally how to run a web server to service that time. Of course, you could be doing all kinds of things with that web server, but you know that the time is right and you can access the NeoPixel. So quite a little demo here, but it does quite a lot of things to show you all the basic things you might want to do with your Challenger board, this time using the Arduino IDE. Okay, so there it is. Now I think you'll agree with me, that's a really versatile board. Now the point is this, is it's more expensive than the Raspberry Pi Pico W, but not by much. Considering you get that 8 megabytes of flash USB-C, you've got the NeoPixel, of course you've got the Wi-Fi, the Bluetooth, and you've got the charging circuit for batteries. This thing actually only costs 15 euros, which is actually a pretty good price when you consider the feature set. I'll leave a link, of course, to where you can get it in the description below. Okay, that's it. My name's Gary Sims. This is Gary Explains. I really hope you enjoyed this video. If you did, please do give it a thumbs up. If you like these kind of videos, I invite you, I implore you, stick around by subscribing to the channel. Don't forget you can follow me on Twitter at Gary Explains, and I also have a monthly newsletter. Go over to garyexplains.com, type in your email address, no spam, but you will get the email. Okay, that's it. I'll see you in the next one.